Welcome back. This video will be about a tutorial on how to design a rotor blade. Now this rotor blade will be very simple. There's no twist to it. So before we design it, let's give credit to the paper from which we are referencing. So this paper titled Effects of Rotor-Rotor Interaction on the Wake Characteristics of Twin Rotors in Axial Descent was written by, I'm sorry if I didn't pronounce it right, Siupong Chai and the others. They're from Department of Mechanical Engineering in Republic of Korea. So I'll go straight to where we'll be getting the references from. Now this is the rotor blade we're designing. The F-oil of the rotor is Naka 0020 and it has a pitch of 20 degrees and a wingspan of 80 millimeters. It's a pretty small rotor blade. So first of all, let's go ahead and get the let me just write down the steps. So the first step we'll be doing is to get the F-oil, the rotor blade. Then we design the rotor blade in CATIA. Then to do the simulations, if we still have time, we will do simulations in Xflow. Simulations in Simulia. These are the basic things we'll be doing in this video. So first of all, let's get the F-oil of the rotor. Now rotor blade is consisted of few F-oil sections. Likely there's only one F-oil that is used in the span-wise direction. So, and that is Naka 0020. To get this F-oil profile, we'll have to Google and write F-oil generator. Just click on the first one. Now from here we can see it's Naka 2412 F-oil. This is the profile, so we don't need this one. We check for Naka 0020. Yeah, we got this. It's Naka 4-digit F-oil generator. Naka 0020. Click on it. Yeah, this is the F-oil profile. So number of points 150. That's number of points over this one, the suction side and the pressure side. So let's just increase the value up to 200 and we close the trailing edge. If it's open, then the pressure side and the suction side won't be closed at the end, at the trailing edge. This is the leading edge and this is the trailing edge. So once we close, open or close, TE means trailing edge. So we close it by ticking this one. Then we just click plot. Okay, nothing much has changed, but we just increased the number of points from 150 to 200. Now we send this to FOL plotter. Alright, now we'll change some values here. For example, if we go back, not here, oh yes, to the, sorry, wait. If we come here, we can see that, let's read further down, the rotor model. The radius and the constant chord length of the rotor blade were 40 and 16 millimeters respectively. So rotor blade, from the radius is from the rotation hub to the tip of the blade, it's 40 millimeters, and the chord length is 16 millimeters. Therefore chord in millimeters should be 16, and here the origin is 0%. That means it starts from here. So I think when we're designing in CATIA, this has to move somewhere here. It's also convenient to be here, but I like it when the origin is in the center of the FOL. So I'll bring it to 50%. Later when I say plot, you will see this one moving up around here in the center. Now pitch in degrees. Draw the blade cross section of a knockout 0020 FOL, which we already said, and constant collective pitch angle of 20 degrees. So that is pitch in degrees 20. So that's basically what we need to design. Moreover, rotor blades composed of ABS-like resin fabricated using ore. This is a material system. So plot. That is the cross section of the FOL that we need. Name is NACA 0020, and the chord length is 16 millimeters, and the origin is 50%, which is in the middle, and we have a pitch of 20 degrees. Now we'll click this one, CSV file of coordinates. So it automatically downloads this. So we would come to this. I would just copy this one, and I go to my desktop. Let me create a folder. I'll call this Rotor Design Tutorial. Then I paste it here. Now, since you're using CATIA, there's a format of Excel that CATIA reads. So this, let's see the coordinates first. These are the X and Y coordinates. Therefore, there's a special Excel format which CATIA can read. So we will make some adjustments to this CSV file. In order to do this, I have a format that's already saved, so I'll just get it from there. Yeah, it's this one. Copy. What was it? It's here. Paste it here. So this is the Excel format that CATIA reads. GSD point spline loft from Excel, I think. Yeah. So first of all, I open this one, and let's open both of them. Yeah. All right. Notice that we are sketching three-dimensional foil. So we see that the XY coordinates are given and the Z is not given. So we'll add the Z column as well. However, there's a thing that we should know. If you are sketching from you're sketching perpendicular to the X, Y, or Z axis. So here I'm sketching perpendicular to the Y axis. So I'll make the X coordinates 0. But first of all, let me copy this. Okay. Don't worry about all this X, Y. Just start copying from the numbers. Until you reach the end. Don't worry about the rest. Copy it here. And probably just paste it right for a second. Now this is X, this is Y, the Z should be here. But what I'll do is I'll make this X, I'll make this Y, I'll make this Z. So I'll make this X0. Double click. Then I'll copy all this into the other Excel format which CATIA will read. So close this. I think, yeah, it's this one. So this is from my previous design. I'll have to delete this. And sorry, I'll bring in my new coordinates. Let me copy and paste. Yeah. Let's check if it fits well. At the beginning, it should be like this. This format should be there. And at the end, you should have this. Now we save this file. Let's minimize it. We close this. Don't save. And let's go and open CATIA. I don't really use SolidWorks, so I'll just use CATIA. I have two versions, but I like using the 55R20. Let's wait for some few seconds. It's very slow. No, very slow. Oh my days. Okay, I'll begin by clicking start. I'll do this in mechanical design and part design. Rotor design tutorial. Click OK. Once this is open, first you leave CATIA open to this page. Now you minimize it, go back to the Excel file. Hold on, first this is done, highlight it. Now we're in the second step. Second step, come to Excel file and click, bring the cursor and click here in this box. Then you'll come to view, macros, view macros, click on main, click run, and insert 2. Okay. Now it's automatically exporting these coordinates into CATIA. Wait to finish. Okay, once it's done, you can close it and open CATIA. To maximize in CATIA, you press Ctrl and click on the roller. Is it called the roller? On the mouse, and you push forward. So we have all these points. From here, let's hide the points. Come to tools, hide all points. Now this is the airfoil. However, this doesn't seem like a perfect curve. It has some edges, some corners. So I think that's an issue in CATIA. We have to fix this. Come to, is it standards? Options, I think. Probably in options. And display, performance. Under performance, we would click on proportional, bring this down to 0.1, and proportional as well, bring it down 0.1, and click OK. Now you see the curve is very smooth. From here, let's go back to the reference. The reference tells us that the radius of the rotor were 40. Here to here is 80 millimeters, so the radius should be 40. So in that case, we'll create another plane 40 millimeters from this center plane. To do that, there are some of these tools they're hiding, so we click and drag inside. Yeah, this is the tool that we need. We click on XY plane and click on this plane. So since it is 40 millimeters in radius, we'll have to create a plane 40 millimeters away from the center. Yeah. Once we have this, we will just project this one onto this plane. To do this, since we're projecting onto this plane, we click on this and sketch. If you can't find this, I think it's fit all in. Yes. Then come here and click project 3D elements. Click on it and click on the F1. Once it turns yellow, you exit Workbench and you will see that this one has been projected on the other plane. Now, for us to create a wing, we have to at least connect a line from a point to another point on the other airport, so that it will act as a guide for us when we are performing the multi-section solid. So in order to do that, we click on this. Hold on. Alright. Now we hit a very important point here, the center point of this airport. So I would go back and think it's the 100 and no, the safest way to do is to go back and we'll look at the center. Copy this. We're just looking for the center, so paste it here. Then check how many coordinates are there. This is 201 coordinates. That means we have 101 is the center. Point number 101. This one should be the center point. It divides 100 to that way and another 100 to that way. And this is the center coordinate. So we head back. We close this. No. So we look for point 101. Click on it and show. and then we click on this point again. Sorry, the plane. We'll project the point to another plane. Exit the web. Now it's easier for us to connect the two lines. The two dots. So we come to this line, click on this point, and it automatically clicks on the other point. Okay. Since we are done connecting this, we'll come and say multi-sections solid. Click on this, click on this, click on this, and click here. The guide should be this. Click on preview. Okay. This is one side of the wing. Yeah. And we need to design the other side. First of all, check the design. You can see that in this design, the leading edge are pointing in the opposite directions of this wing. It's very typical of propellers or any rotor blades. So to do this, we would come and say circular pattern 2. We select the y-axis. Is it the y-axis? I think it's the z-axis. And give an angular spacing of 180. Now we see from the top view. Oh no. Where's top? Is here. Yeah. It looks good. Now there is one thing. When we are doing simulations, there are some countries that have their own, I think, rules and regulations of the way in which the propeller or rotor blade rotates. I think the American system, it rotates in a counterclockwise direction. And from this design, we can see it's rotating in the clockwise direction. So if we are to design a system that is based on the American or European standards, the leading edge should face this way from this side, and the trailing edge should be that side, so that the rotation would be in a counterclockwise direction. But for simplicity of our design, we would not consider that. Now let's create the rotor hub. Click on this one, and which plane is this? The XY plane. And sketch. since the chord length was 16 millimeters, we'll give a radius of 8. Okay, this is diameter, so yeah, it's 16. Since it's not given, since the radius of this one is not given, we just keep this 16, and let's give a breadth to this. Let's mirror the extent, probably thickness of 4. Preview. Yeah, looks good. And let's create a hole of, since this is 16, sorry, 8, that's diameter 4. Okay, that's basically a rotor plate we just created. Now for us to export this into software like Xflow Simulia, we would export this as file, save as desktop, with rotor design tutorial. ITS. Is it ITS? Let's see. Rotor tutorial design. Save as ITS. I get over here. Check this. Really? Uh-oh. Made a mistake. Shouldn't have clicked on it. Hold on. Close this nonsense. Yep. Let me check from my previous STL. My goodness. We save this as STL file. Save. This is a nonsense. This one is. Yep. That was the rotor we. Let's see. The street viewer. Oh, this is the one. So that's basically the most basic way of how we can design a rotor blade system in CATIA. So this is done. For the third one, simulating this, I don't think it's necessary. But if you guys think it's necessary for a tutorial, we'll do it in the next video. Thank you guys for watching and have a nice